vector equation of a line. Okay, so we're going to take a look at this. I've drawn a bunch of stuff out here for you. So let's take a look at it. We're using the same line that we had before. Y equals negative 3x plus 2. Okay, so y equals negative 3x plus 2 in this one. Okay, and it goes through 2 on the y-axis, has that point 1, negative 1. But I've also drawn in a couple other vectors. So I've drawn in that direction vector. The slope vector m goes from the origin to that point 1 comma negative 3. And I've drawn in another vector. I'm calling it r naught. It's in blue. It's a vector from the origin to some point on the line. We know this point. Now, if I combine these two, m and r naught, okay? So if I just take r naught plus 0m, it's just the vector r naught. That vector ends at a point on the line. If I take m plus r naught, so m along here, and then add r naught to it, it's like I'm going parallel to the line and then I'm shifting up to the line with the vector r naught. That gets me a point on the line. If I go 2m plus r naught, I get a point on the line. If I went 3m plus r naught, I'd get a point on the line. If I went negative m plus r naught, I get a point on the line. And these red lines here would seem like they're all fanned out from the origin and they all end at the line. So you'd have sort of this barrier where these red lines all end at, and that's the line. And this is where we get the vector equation for the line. So first we're going to define m, the direction vector, is any vector that is parallel to the line. So I could use this m, or I could use the opposite direction, or I could use a vector twice as long as it's parallel to the line. R naught is a vector from the origin to a fixed point on the line. So that's the point I chose. I could have used this point. Then I could have went m plus that r would have got me to that point. They all would have ended at the line. Okay? And then we can define our vector equation of the line is going to be r equal to r naught plus tm. Okay, so this is a vector equation of the line where r equal to xy is a vector from the origin to the points on the line. Okay, so r is a vector from the origin to the points on the line. So r is not a point, it's a vector. So we've got to keep that in mind in the vector equation. R is not a point, it's a vector from the origin to a point on the line. Okay. So for line L, the y equals negative 3x plus 2, we have it in slope-intercept form and we have it in parametric form. In vector form, m is just 1, negative 3, or any scalar multiple of 1, negative 3. And r naught is some point on the line, so it's 0, 2 in this case, or any other point on the line would have worked. And then we can write the vector equation of that line L as r, or x comma y, equals 0, 2 plus t times the vector 1, negative 3. Okay. Now we can come up with other forms of this. We could have written these two. So you might want to take a minute to try and justify them before I explain it. So if you pause the video now, you'll be able to think about this. Okay, so the vector r could be 1 comma negative 1 plus s times 1, negative 3. We know that 1, negative 3 is a direction vector for the line, so that's going to work. And if we go back to the graph, 1, negative 1 is a point on the line, so I can use that. So a vector from the origin to that point. Okay, and we also know that any vector parallel or collinear with 1, negative 3 is going to work as a direction vector. So let's multiply that by negative 2, and we get negative 2 comma 6. So negative 2 comma 6, and it goes through that point. that's parallel to the line, that's a point on the line. This is going to give us the equation of that line in vector form. And k is the parameter in this one. Okay, so I'm going to stop the video here, and we're going to get back to Cartesian form.